Alright, so here we go with the intro video for the entire topic of series. I always like doing this at the beginning of every chapter just to put everything into context so you know what you're getting into. Maybe it'll even be interesting to you. I think this stuff is really interesting, but hopefully you do too. I mentioned this in the intro video for the solids of revolution, but you finished calculus, I'll say what I mean by that, at the end of chapter 1 of Calc 2. That's the integration by parts, trig sub, trig integrals, etc., partial fractions. What I mean by that is calculus is the study of derivatives and integrals. In Calc 1, you talked about derivatives and you learned how to do them. You learned about integrals. Calc 2 was how to do them, and now you're learning about different ways to apply them. What are these things good for? How do I use them? The first thing you did was talk about volumes. You talked about work, arc length maybe. There were a couple things thrown in there. This is the second big thing that you can do with calculus. Series is an insanely useful tool in calculus. And I want to tell you what it is very briefly. I'm actually going to make, for this one, I'm going to make a part 2 for just the intro section. And then we'll just get into section 1. Because this chapter is a long haul. I'm just letting you know. So, what else is it good for? What else is calculus good for? Well, I mentioned in the very first Calc 1 video, and I hope you remember, that some integrals, like sine x over x, e to the minus x squared is one. There's a bunch of them. Sine of x squared. There's e to the x over x. Some of these integrals are not able to be written down in a really nice combination of sines and cosines and logs and square roots and all, and plus and minus and multiplying. There is no combination for any of these. No function that you can write down will give you a derivative of sine x over x. That's just because we don't have it. This is a pretty limited toolkit. It's not that this integral doesn't make any sense. I mean, think about it. If I integrate this function from 1 to 3, I mean, I don't know what the function looks like, but say it goes up and down like this from 1 to 3. It's got some area under there. That area is a number. You can get a decimal out of it. In fact, if you plug it into your calculator, you'll get an answer out of it. So how do you actually do it? Well, if there's no way to get any of these as an antiderivative, the best that you can do is approximate. That's the best that you can do. So how do you actually approximate it? How does your calculator approximate it? How does Wolfram Alpha approximate it? What do you do if Wolfram Alpha can't approximate it, if it's too hard, too difficult computationally? How would you code something that does this? This is a really, really useful thing to do, and this is what series are all about. The bottom line about series, and I haven't even defined series, but I'm getting there, is that all computers know how to do is plus, minus, times, and divide. Anything else that it does is some combination of these. I mean, it's zeros and ones. This is literally only what it can do. So when you ask it to put in your calculator sine of 42 degrees, do you think it's going into its system and drawing a triangle and trying to find the opposite and hypotenuse? Like, how would it even do that? It gives you an answer. I don't know what it is, but like 3, 2, 4, 7, 0, 1, 8. It's not right, but it gives you a decimal. How does it do it? This is all it knows how to do. Think about what kind of objects you can build from these operations. It's polynomials, isn't it? I can add different things. If I take an x, a variable, if I apply these operations to it, I can multiply, I can add, I can do exponentiation, because that's just repeated multiplication. I can subtract. I can divide by numbers. This is what a polynomial is. I can add 17x over 9, and then I can do the third power to all of this. Then I can multiply it by a half. I mean, these are all polynomials that I'm getting out of this. So somehow, all of these extra operations, tangents and logs and e to the x and square roots and everything your calculator does has to be it has to be a polynomial, which kind of feels contradictory. So now I'm going to show you exactly what that looks like. So I'm going to share my screen. Going to get these out of the way. So I do not want you to know how I come up with this, how I come up with these polynomials, but I want you to check this out. Here is e to the x, just a pretty easy function. I'm going to check out the function 1 plus x. There's a line. Then I'm going to add x squared over 6. There's a parabola. Okay. Sorry, x squared over 2. Then I'll add x cubed over 6. Oh, that's weird. Kind of looks like e to the x up here. Plus x to the 4th over 24. Don't worry about how I'm coming up with these numbers. This is what we're getting to. Oh, it looks a lot like e to the x now. How about I'll add an over 120 to the next one. Now it's pretty close. I'll do one last one. If I put 720 on the last one, it even looks even more like e to the x. So this blue stuff on this part of the graph, this part right here, is basically the same as e to the x. In fact, to show you, I'm going to call the e to the x f in Desmos, and g to the x. I'll call the polynomial that I wrote down just a 6th degree. I'll call it g. If I give f of 1, that'll give me e. 2.718 to it. Okay, fine. But check out g of 1. That's pretty close. I got 3 decimal points right. The name of the game is that your calculator, or Wolfram Alpha, or whatever it is, when it asks you to calculate the square root of e, let's say, I need x equals 1/2 because it's e to the x. What is Desmos doing right now when I put in root e and it gives me a decimal? X equals 1/2. It takes a polynomial that is close enough. Sorry, do g of x, and then I'll do f of a half. That's the square root of e. Check out g of 1/2. That's the polynomial that's supposed to be super close to it. 1.6487. I got 4 decimal places right. So what your calculator is doing is it's adding, and as I add more terms on here, if I do a 7th degree, if I do an 8th degree, if I do a 10th degree, 15th degree, I will get closer. I have to know what numbers to put down here, but I have to get closer and closer and closer. So your calculator only has so many digits in its entry that it can give you. So all it does is it takes a polynomial with enough terms in it so that you can't tell the difference, and it gets the answer right up to that many decimal places. So polynomials end up being a really important thing. So the big question of the unit: how do we write functions as polynomials? And we're going to explore that in the next intro video.